Stufken from University of Georgia. He has given a wonderful talk yesterday, and he has highly agreed to give another talk on crossover design today. Let us welcome him.
Thank you very much. So when I was asked to give two talks, one question was, of course, what are the topics of the talks going to be? And briefly, I was considering to talk about design for functional magnetic resonance imaging data and experiments. But then I said, well, the expert is actually here, so let's not talk about that. Let's talk about something else. So I'm going to talk about crossover designs. And it's a topic that I have worked on off and on for a long period of time. And here are some of my collaborators on papers that I have published on this topic. Stufken-22Mar was a student at the University of Georgia. I'll say a little bit about that work later on. There's a paper in the Journal of Biopharmaceutical Statistics that I published with Sam that is very closely related to this particular talk. There will be some results of these two papers which are published both in the Journal of the American Statistical Association with Joachim Koenert from the University of Dortmund. If you were in my talk yesterday, one of my the main collaborator with that topic was Mei Yang, and I also worked with him on crossover designs. And then I have a paper that I'll talk briefly about also today with Masumi Bose on a particular model for analyzing crossover data from crossover experiments. So I'll give you an introduction. I talk a little bit about the different models. My talk will focus on comparing only two treatments, even though some of the results that I'll talk about are generalizations for more than two treatments. And then I'll talk, if time permits, I'll talk about estimators and subject dropouts, and we can do so. So, first of all, what is a crossover design? Not everybody may know what a crossover design is. So here's an example. What's typical in a crossover design is you have a certain number of subjects. That could be people in a clinical trial, there could be animals in a dairy experiment, for example. In fact, this data was from an animal science experiment where the subjects were cows. And each of these subjects is observed at multiple time periods. But not only observed at multiple time periods, but you can assign different treatments at multiple time periods. So these treatments in this particular experiment are actually different diets. So these cows were being compared when being fed these different diets in terms of the milk production. The measurements of our milk production. These were cows during their lactation period. So the entire lactation period was split into 3 time periods with each cow. And during the first of those time periods, cows used one diet, the second diet was the second period. And at the end of each of those periods, the milk production was measured. So that's typical for a crossover design. You have multiple subjects, but each of these subjects, you assign more than one treatment to each of these subjects. Different treatments in different subjects. Now, in this particular example, this is a very special design. It's an example that's called a uniform balanced crossover design. The uniform refers to the fact that each subject receives each treatment, each diet, exactly once. And also, if you look over the periods, in every period, you see each diet appear equally often, twice. That's what uniform refers to. The balanced refers to this. If you, for example, look at, let's say, treatment A, every time that treatment A occurs. Right. What's the treatment that appears immediately before treatment A? Well, here there's nothing. Here's treatment C, here's treatment C, there's nothing here. Here's treatment B, and here's treatment B. So each of the other treatments comes equally often just prior to treatment A. And that's not only true for treatment A. If you look at treatment B and you see what comes immediately prior to treatment B, you see that each of the other treatments, that's A and C, will come exactly twice, just prior to B. And the same story holds for treatment C. That's what the balance refers to. And we'll see in a moment why that may be important. Well, that could be a desirable property for designs to have. This, by the way, is from an experiment that was conducted in, I think in the late 1940s in Ames, Iowa, Iowa State University, and it's published in a paper in 1949, and also in a book on design experiments by Cochran and Cox. Here's a second example. This is comparing an active treatment with a placebo for the prevention of acid reflux in patients with GERD disease. So this experiment had 12 patients, so these patients were subjects. We had the two treatments, one being the placebo, one the active treatment. And each of these 12 patients, there were 3 that received this sequence. Treatment A in the first period, treatment A in the second period. Same treatment. So it doesn't always have to be that every subject receives every treatment. You can repeat treatments. 3 subjects received this sequence, A, B, 3 B in the first period, A in the second period, and 3 of them received B, B. This is something that people call a strongly balanced design, and I'll skip the definition because it's not going to be very important for this particular talk. But it's another example of this type of experiment. So this was published in 1989. And of course, so you may wonder, what do you gain by having sequences like this, A, B, B? Wouldn't it be better to have maybe 6 of the subjects receive the sequence A, B, and 6 of the subjects receive the sequence B, A? Does that make more sense? Because after all, what we're trying to do in an experiment like this is compare A to B, placebo to the active treatment. And wouldn't you do a better job if you make such a comparison on every subject? Because if you use this design, then some subjects you cannot compare A to B anymore. You have information about the treatments in that subject. And it turns out actually that depending on what kind of model you use, that in some situations this design is a better design to use. And this, in other situations, it's not. So it very much depends on what you believe to be true about the model that you use for analyzing such data. And we'll talk about different models in this talk. So crossover designs have multiple uses. They're especially popular because of the use in the pharmaceutical industry, in drug development especially, where in the earlier phases, experiments are relatively small, there are relatively few subjects available to do the experiments. And what people try to do then is, with a small number of subjects, they'll try to use each of these subjects more often than once to get some information about different treatments. Now, in general, the number of treatments and periods does not have to be the same. In my 2 examples, they were the same. In the first example, we had 3 treatments, 3 diets, and 3 periods. In the second example, we have 2 treatments and 2 periods. That does in general not have to be the case. So you could have crossover designs where you have 2 treatments, where you have 3 periods, or more than 3 periods. So we talk about that as well. So the design question here is, for a given number of periods, for a given number of subjects, and for a given number of treatments, what sequences should we use in the experiment? Right? I showed you this small example with the AB and the AA, with two possible designs. Which of those designs is better? Well, that's a general question, right? I mean, if you have 2 treatments that you want to compare, 3 periods, and you have 6 subjects available, what sequences are you going to use? You can use the sequence AAA, you can use the sequence ABA, ABB. There are a bunch of sequences that you could use. You can use all of them. You can also use only some of them. What is a good design? Which one do you use? And what I said here, we will actually focus on a slightly different question. For those of you who were at yesterday's talk, that slightly different question is related to something I was talking about yesterday. That rather than talking about I have 6 subjects and I'm going to use this sequence once and this sequence twice, I'm going to talk about the proportion of time that I use a sequence. So I'm going to say, forget about the number of subjects. I'm going to use this sequence for half of the subjects, no matter what that number of subjects is. I'm going to use this sequence for 1/3 of the subjects, and so on. So that's really the question that we're going to talk about when we talk about good designs. Now, before talking about good designs, let's talk a little bit about pros and cons for when using crossover designs. One of the pros is obvious. I mean, we need fewer subjects to get the same number of observations compared to a parallel trial. In a parallel trial, you would get a single observation, a single treatment from each subject. And so if you have now p periods, if you have, let's say, p periods in a crossover design, then you need only 1/3 of the number of subjects that you would need in a parallel trial in order to get the same number of observations, the same application for the treatments. The other advantage that's immediately clear from a crossover design is that treatments can be compared to the same subjects. And you would expect that such comparisons are more precise than comparing treatments on different subjects. Because if subjects are different, whatever comparison you make can be confounded, can be a larger uncertainty because of differences between the subjects. So if you can compare them with the same subject, you should get better estimates for the differences between the treatments. And those are 2 clear advantages of crossover treatments. But because a crossover design is not suitable if the treatment that you give a patient really changes that patient, maybe cures the disease or kills the patient. In a situation like that, you cannot use a crossover design. So the crossover design can only really be used in a situation where you have something, you give that patient a treatment, but it doesn't really change the patient. It leaves the patient the way it is, maybe for a chronic disease. The duration of the experiment with the crossover design will tend to be longer. You have more periods now. You have to use each subject multiple times. So you tend to get a longer experiment. And if it's too long, then that's going to maybe affect or create some dropouts. A patient that comes in for the first period, in the clinical trial, a patient that comes in for the first period, maybe even for the second period, but then says, no, this is not helping me, I'm still feeling miserable, I'm going to give up, I'm not going to come anymore. So if you have too many periods, there's a good chance that you get dropouts and you get missing data, that you have to deal with that. So as a result, typically what one sees is that the number of periods is relatively small, especially for the application in the pharmaceutical industry. 2 periods, 3 periods, or 4 periods, those are the most common numbers. The other thing you have to worry a little bit about is covariance structure. You have now measurements that you're making on the same subject. It may not be reasonable to assume that those are independent. So there may be some dependent structure. And for the analysis, there's maybe you can handle that easily. You can estimate covariance matrices, or maybe parametrically or non-parametrically. But at the design stage, that's of course much more difficult because you don't have data. You don't have anything to. You're trying to say what a good design is, but if the data are correlated, then the answer may depend on what that correlation structure is. And if you don't have data to study that correlation structure, you don't know what it is. So either based on prior information, or maybe by some guess, by using simple parametric model, maybe an AR1 process, for example, you try to make some progress in that if you try to take it into account at the design stage. The other complications, the baseline measurements could be available in crossover designs, and then you have to decide how you use those baseline measurements. The baseline measurements would be that prior to a period, you have some information on the subjects already. So it's not only that maybe maybe suppose an experiment where the response variable is blood pressure. Then you measure the blood pressure after you give this subject treatment, but you could have measured the blood pressure before giving the subject treatment as well. So that would be the baseline measurement. And that would then be used to take into account that these subjects are different. There are differences, natural differences between the subjects. So you hope to get a better comparison of the effect of the treatments by taking these baseline measurements into account. And baseline measurements could occur only before the first period, but it could also be that you have baseline measurements before every period. And so there are different ways of then trying to take sort of baseline measurements into account. I'm not going to focus on that in this talk, but I have a student who graduated about 6-7 years ago who actually worked on this problem, looking at different ways to take baseline measurements into account. One thing that I do want to focus on this talk is the carryover effects, and that brings me back to this picture. See, the models that are being used, one thing and that's a problem, a potential problem with the crossover designs, is that, for example, if I make a measurement over here, in this period, this 39 that I'm measuring here. So it would be normal to have a model that says, well, maybe it has, to some extent, is affected by the period in which the measurement is being made. So you have this entire lactation period, well, towards the end of the lactation period. If you look at this data, you probably can even see that. Towards the end of the lactation period, the milk production naturally will be lower than it was at the beginning of the lactation periods. And you can see that this happened in this experiment, right? Towards the end, you get smaller numbers here than you got at the beginning. These numbers are some measurement of the milk production. They're coded measurements, but smaller numbers means less milk production. So the period effect could be present, so you want to take that into account in your model. There could be an effect due to the subject, a particular cow, to which this observation is being obtained. So you want to take that into account in your model. You would expect that there's an effect that's due to the treatment that's being given over here. So you want to take that into account in your model. But what can also happen with crossover designs is that maybe there is still an effect, a lingering effect from a treatment given in the previous period. Maybe C. Maybe even from treatment given in the first period. And you have to think as to whether you need to take that into account in the model as well. And so that's why what people have often done is they have said, well, let's forget about earlier periods, but at least the previous periods, maybe we should take that into account. And that's why this balance that I talked about here becomes important. Because now it's not only the treatment given in the current period that becomes important, but also the treatment given in the previous period. And so that balance that we talked about here, that we demonstrated here in this design, that makes things a little bit easier in terms of analysis if you have this balance, but it also turns out to be good in terms of as a property for the designs. So these carryover effects from the previous period is something that you need to be aware of, and it's something there's a lot of discussion about in the literature as to how you should handle such possible carryover effects. Now, the next slide, we'll have some more on that. So in terms of dealing with carryover effects, there's broad agreement that they can appear in such experiments, in these experiments of these crossover designs. But there's much discussion how to deal with it. And a lot of the discussion focuses on this very simple design where you only use the sequences A, B, and BA. So 2 periods only, half of the subjects receive AB, half of the subjects receive BA. And there's several proposals on how to deal with it, and none of them seem to be very good. The conclusion to some extent is that washout periods, and washout periods are periods of inactivity between the active periods. So you have the first period where the subject receives the treatment, then there is a period of inactivity, and then there's a second period where the subject receives the treatment. So washout periods then are meant to allow the treatment given in the first period to wash out the system of the subject, so that the subject gets back to being him or herself in the second period. And so many people say that if you use a crossover design, you should be sure to use washout periods, and be sure that those washout periods are long enough to wash out whatever carryover effect there is. That's the only time that you should use crossover designs. That's what some people say. And I think that there's broad agreement that washout periods are very important, and they should be used whenever possible. But first of all, they're not always possible, because inactivity, well, suppose that this is a patient suffering from some chronic pain. What do you say during the washout period? Sorry, I can't give you treatment here because you're in a washout period. So you don't want to do that. You want to give these patients some treatments. The other issue is that you don't always know what a long enough washout period is. How long should that washout period be so that the drug given in the previous period completely washes out of the system? You don't always have that information. So it's not always clear that even if you do use a washout period, that your washout period is long enough. So for that reason, there are also people who have advocated that you should use a model that includes carryover effects in the model, so that if they are present, that you can account for them in the analysis. Some people are very much opposed to those models. They have called these unrealistic and harmful. And there's also been some criticism about these models, and I'll come back to that later on in the talk if time permits, that the estimator that you use, because if you have a carryover effect in your model, then if you want to now estimate the difference between the treatment effects, you typically have to adjust that estimator for the presence of these carryover effects. And so what people have said is that this adjusted estimator that adjusts for the presence of carryover effects, has vastly increased variance compared to the estimator that you would have if you did not have to adjust for carryover effects. And that claim turns out is not always true. Whether that claim is true or not depends on which model you use it and on which design you use it. And so for some designs, this claim is simply not true. But again, we'll come back to that, so hopefully if time permits. So I have already said a little bit about model terms. The treatment that's used in the current period, I will refer to that as a direct treatment effect. Treatment that's used in the previous period, I will refer to that as a carryover effect. And again, I'm going to limit myself to only the treatment in the immediately preceding period, not 2 or 3 periods back. And if that's the case, then you're really in trouble with carryover effects. Period effects I've already mentioned to you. Subject effects I have already mentioned to you. Some people use sequence effects, and I've never understood what they are, so I'm going to dispose of them. But then there are other effects that people include in the models, the sort of interaction terms that are sometimes being included. So this is a treatment by period, or treatment by subject interactions. And sometimes that's a reasonable thing to do. But you know, degrees of freedom are limited. These tend to be fairly small experiments, small number of subjects, small number of periods. So you can't have too many terms in your model. So I'm going to limit myself to fairly small models with a fairly small number of these terms, typically direct treatment effects, carryover effects, period effects, and subject effects. Now, the subject effects, there's some question as to whether you should consider them to be random or fixed, and I'll say a little bit about that in just a moment as well. So here's some of the notation. I'll use P for the number of periods, and T for the number of treatments, and most of this talk is about two treatments, treatments A and B. So I have a response, which I call YIJK. It's the response in the ith period for the kth subject assigned to sequence J. And I'm assuming that my response is continuous. So if you have binary responses, then some of these design considerations here don't apply. The problem of choosing design is a different problem. By Dij, I'll denote the treatment using the ith period for the J sequence. And then we have the period effects for i's. We have subject effects. So this is the effect of the kth subject assigned to the J sequence. We have the direct treatment effects, denoted by taus. And so this is just a particular treatment. And we have carryover effects, and forget the dot, 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 and it's just the first order carryover effects. So it's the effect of the treatment, and I'm using gamma here in notation, it's the effect of the treatment for the previous period onwards. And then random errors. I'm going to assume that the subject effects are fixed, which, if you do the analysis, you probably don't want to do. In the analysis, you probably want to assume random subject effects. These subjects, like the cows, for example, in my first experiment, you probably want to think of them as randomly selected from some larger population, and your inferences are for that larger population. On the other hand, the information that you get about treatments in a crossover design, most of the information you get from comparison within subjects, from comparisons on the same subject. That's the most precise information that you can get about differences between treatments. So in judging the designs, I'm just going to use that. And that's the same as saying that take the subject effects fixed and see simply what information you get within subjects. So in comparing the different designs, that's all I'm going to use. Because comparisons between subjects, the information that I get about that for differences between the treatments is going to be very limited. So I don't care too much about it. That's why for the design stage, I'm going to take my subject effects as fixed. And I'm going to assume that my error terms are independent. And that's something that one can certainly criticize, as I have already pointed out, that maybe that's not a realistic assumption. But from the other hand, at the design stage, I don't know what is the realistic assumption, and if independent error is not realistic, then what is it that I should assume? And if I assume something that uses some parametric model for the various covariance of these error terms, that means I'm also introducing additional parameters that I don't have any information about, or little information about. So I'm not sure that the problem becomes more manageable if I assume a different error structure. Now, if I have strong information that this is the wrong error structure, then I probably shouldn't do this. But I'm going to assume that the errors are. And here are 4 different models. The first one is the model that has no carryover effects in it. So it's just period effects, subject effects, and direct treatment effects. Then the second model, which I'll refer to as a traditional model, the same as the first, except it has this additional term for the carryover effects. So it has the carryover effects from the previous period. Where in the first period, for those observations, there is no carryover effect, because there was nothing before the first period. So observations in the first period have no carryover effect, but observations in later periods have this carryover effect from whatever the treatment was that was given in the previous period. So another way of modeling carryover effect that people have proposed is through this model, where carryover effects are proportional to the direct effects. So the first terms are again the same as this initial model, but this additional term here is different here. And the assumption here is that the carryover effect, the effect from the treatment in the previous period, is proportional with a constant proportionality to theta to the direct treatment effect, to the taus. So what this is saying is that if a treatment has a strong direct effect, then it also has a strong carryover effect that will linger longer as well. And for some applications, this may be a reasonable assumption, right? That the carryover effect is related to the direct effects in this way. That if the direct effect is strong, then it also will take longer for it to wash out of the subject's system. And then the last model here is again a variation that's based on modeling the carryover effects in a different way. Rather than just have a single carryover effect as in this model, there are two different carryover effects now. There is something called the gamma M, and there's something called the gamma S. And gamma M refers to mixed carryover effects, and gamma S refers to self-carryover effects. So these things are, again, carryover effect from the treatment in the previous period, except you see something in front of these terms now, this delta ij and 1 minus delta ij. It looks very complicated, but it is very simple. Delta ij is either 0 or 1. It's an indicator variable. And when delta ij is 1, then this term here disappears. It's not there. And so you only get this term, this guy. If delta ij is equal to 0, then this term disappears, and this becomes 1, so you get only this guy. So the model still has only a single gamma each time for each observation, except it may be different gamma. Sometimes this is gamma M thing, and sometimes this is gamma S thing. And what does that depend on? Well, this delta ij is equal to 1 if the treatment in the current period and the treatment in the previous period are different. And it's 0 if the two treatments are the same. So what we allow here for is that the carryover effect from a treatment in the previous period does not only depend on the treatment in the previous period, but can also depend on the treatment in the current period. If the two treatments are the same, then the carryover effect can be different in the situation where the two treatments are different. And this is essentially a model that was suggested, though not studied, by Fleisch in 1989. That was part of his criticism that these carryover effects should not just depend on the treatment in the previous period, but maybe also in the current period. And so this is a model that takes that into account. And for the situation of two treatments that I'm considering here, in fact, this model is a parameterization of a model that includes a full interaction between direct and carryover treatments. So those are the four models that I'll talk about. So either no carryover vector volume model, or this traditional model, which simply says there is, for each treatment there's a single carryover effect. It doesn't matter what treatment in the current period is, it only depends on the treatment in the previous period. Or this model, which says the carryover effect is proportional to the direct treatment effects. Or this model, which says the carryover effect not only depends on the treatment in the previous period, but also depends on the fact that in the current period we use the same treatment or we use a different treatment than that in the previous period. So let's go to design. So I want to show you some results, but without going into the technical details as to how those results were obtained, about efficiency of different designs for estimating the difference between direct treatment effects. And since I'm only focusing on two treatments, A and B, what I'm really interested in is, of course, this guy over here, the variance of I like to look at the best linear unbiased estimator for tau A1 and tau B, and look at the variance of that, and somehow come up with a design that makes that variance as small as possible. So the optimal design would make the variance as small as possible. And so I need to have the tools to identify the optimal designs. And I'm not showing you the result. The papers that I showed at the beginning, several of those papers, helped to identify these optimal designs. And I will consider in my tables that I'm going to show you a whole bunch of different designs. And I'll give you efficiencies of those designs. And these efficiencies are computed as ratios of the variances, the variance for the optimal design, the variance for this expression, or this variance expression for the optimal design, compared to a similar variance expression, but now for the design that's being considered in the table. Is this a reasonable design or not a reasonable design? So the efficiency is simply ratios of two such variances. One for the optimal design, one for the design under consideration. I say, I'm not showing you, but that's the work that's done in those papers to identify which design is the optimal design. And that can be turned out to be quite difficult for some of the models. But here's one of the tables that I wanted to show you. So to explain the table, first of all, there are a bunch of models, and there are more models than I showed you earlier. So T is for the traditional model. This is for the model with the mixed and the self-carryover effects. This is for the model with the proportional carryover effects, carryover effect proportional to the direct treatment effect. And I give two values here, one for the constant of proportionality being minus 1/3, and one for the constant of proportionality being 1/3. I think positive constants of proportionality are probably more likely in most applications, but there are some examples where a negative constant of proportionality actually turns out to be reasonable. Then there are two other models here, M and S, and they have to do with this model. So model M is the model where it is assumed that self-carryover effects are 0. They don't exist at all. So if the previous period, the treatment is the same as the current period, then it doesn't have a carryover effect. But it only has a carryover effect if the treatment in the current period is different from that in the previous period. So that's model M. And model S, it's the other way around. The mixed self-carryover effect, the mixed carryover effects are assumed to be 0, while there's only some self-carryover effects. I don't think these models come up as often, but there are some situations where they have been suggested as appropriate models. Then the designs, none of this looks like designs, what I've shown here in this column. What does this mean? ABA, well, that's a sequence. This is all for 3 periods. See, T is equal to 3. So, first period treatment A, second period treatment B, third period treatment A. But that's not the only thing that's being used here. In addition to the sequence that is shown, its dual is also being used in this design. And the dual being the sequence that you obtain by switching A and B. So B the first, A the second, B in the third. That sequence is also used in this design. And so the design consists of use for half of the subject, this sequence, and use for half of the subjects, the dual of this sequence. That's the design that I mean by that notation. And the same for this guy, for this guy. For this guy, we have 4 sequences that are being used. These 2, plus their duals. And each of them is used for 1/4 of the subjects. So what I'm trying to do is I'm trying to give relatively simple designs that use the sequences that are being used equally often, and that use a relatively small number of different sequences. Well, towards the end, you get more sequences. You get 6 sequences at the very end. And as I mentioned, these efficiencies, these numbers in the table, those are efficiencies computed as ratios of these variances. So if you see a 100 somewhere, that means that that design is optimal for that particular model. It's the best design you can use for that. So BAA together with its dual, ABB, each of them using half of the subjects. It's the best possible design for the traditional model. It's also the best possible design for the model that's only mixed carryover effects, and it's the best possible design for the model with proportional carryover effects when they are equally wanted. So if you look for a moment at this table, then you'll probably see some things that jump out, and I think I have marked a few. Zeros. What does it mean that you have zeros? Zero efficiency. What it means is that you can't estimate tau A minus tau B if with this combination of design and model. There is no unbiased estimator. And this assumes, again, that there's fixed subject effects. So there's no information about the difference between treatment A and treatment B if This is the model, maybe MS is the model that you're interested in, mix and self carryover effects, and you use this design, you learn nothing about the difference between treatments A and B. So that would be bad design to use if that is the model that you think is appropriate. So it shows that you better think about what model are you planning to use, and then decide what design you're going to use. Don't just pick a design and say, oh, this is a good design, let's use this design, and then you go to the analysis stage and say, no, let's see, which model should I use? This is maybe the way I want the model carryover effect. And you find out that you use completely wrong design for the analysis that you want to do. So think about it before you do these things. Let's see, why did I mark these numbers? I guess these numbers are just to point out that if you can estimate tau A minus tau B, that some designs have a fairly poor efficiency. So there's a, if you make the wrong choice for design and model combination, then you could wind up with designs where maybe yes, you can estimate tau A minus tau B, but you're not doing a very good job because the efficiency is very low. This one is maybe a little bit more subtle to understand what's going on here. So this is the traditional carryover effects model. And this design is 25% efficiency there. Let's see. If I look at the expected values, if I forget for a moment about subject effects and period effects, I only focus on direct treatment effects and carryover effects, then over here, for this observation, I only have a direct effect from treatment A. Over here, I get a direct effect from treatment B and a carryover effect from treatment A. And over here, it's direct effect from A, carryover effect from treatment B. If I compare this to what happens under the model with mixed and self-carryover effects, I immediately observe I won't get self-carryover effects. I will only get mixed carryover effects because the treatment is never followed immediately by itself. But what that means is that the expected values for all these things that I just mentioned under this model are exactly the same as they were under this model. There's only one type of carryover effect, just as there is on the traditional model. So then why is it that I get a number of 25 here and a number of 100 here if actually estimated for tau A minus tau B is exactly the same under this model as it would be under this model for this particular design? Well, the reason that this is happening is that under this model, I can do much better. So even though we get exactly the same estimated, that means exactly the same variance for estimating tau A minus tau B when I use this design under these two models, it turns out that under one of these models, I can do much better, while under the other model, I cannot. But what that means, of course, is that these two 100s, this 100, my variance is much smaller than it is over there. Because these two variances are actually the same. The variances for the best estimate are actually the same. And obviously this is comparing apples to apples. This variance must be much smaller. The variance under this design must be much smaller by a factor 4 compared to the variance under this design. And so even though I see these different numbers, I say, oh, this is 100. This design is actually doing really well under this model. You can say not so fast. The variance is still pretty big because the variance is just as large as it is under this model for the same design. It just happens that with this model, apparently all of the variances tend to be high. You can't do very well. You can't get a small variance for estimating tau A minus tau B under this particular model. By having these two different types of carryover effects, you're paying a price for it. The price that you pay is you can't estimate as precisely the difference between tau A and tau B. Okay, here is a for full periods. Notation for designs is similar as before. Oh, one other thing I should point out. There's one model that is clearly missing here, and that's the model with no carryover effects. And the reason I didn't include that is that all of these designs perform equally well in that model. All of them have 100% efficiency. They're all optimal in that particular model. So that's why I didn't include it in the table. So here's some of the table for full periods and similar things that I can point out. Some of the efficiencies are low. Again, this model MS, you say, wow, look at this, all these efficiencies are so high. Yes, all these efficiencies are high because there's no design that really does well. Even the optimal design has a very high variance for estimating tau A minus tau B. And so these efficiencies are comparing these variants compared to the variance on the optimal design, and it turns out that nothing does very well. The other thing to point out here, and maybe I have this on the next slide, yes, is that the optimal design under this model is a design that you might not expect. Because in 4 periods, you probably would expect that the designs use each of the treatments twice every sequence. That's not the case. This design uses treatment A 3 times and D only once. So it's a very strange optimal design also. That's the best under this particular model. The other thing that I listed only relatively simple designs. If you look at the column for M, there's no 100. It means the optimal design is a more complicated design than these simple designs. So those tables, they should give you an idea as to, if you have a particular model in mind, you know what kind of design might be the best. But even if you, maybe you should go back and maybe even if you don't know exactly which analysis is an appropriate analysis, you can look at some of those rows and you see that some of those rows, they have efficiencies that are reasonable almost no matter which model is the right model. And so such designs have certain robustness that you don't necessarily have to decide up front as to what the analysis that you want to do is going to be. You can use this design and make a choice later on as what analysis to do. But for example, this last design here, 81, 93, this is not so hot, 83, 81, 78. It's not optimal in any of those cases. It's not unreasonable either. It's not something that it tends, of course, if you have designs with fewer sequences, you tend to get things that go up and down a little bit more. Those designs are much more susceptible to what is the model that you're going to use. They can be excellent on some models and then horrible on the other models. 75, 0, 0, 75, 100, 0, 100, 25, 100, 33, 100. So these are really go up and down. Well, if you use more sequences, you build in some robustness to the design. You don't get optimal designs anymore, but you get designs that perform relatively well for a broader collection of models. So that's another way in which these tables can be used. Now I wanted to come back. How much time do I have? 10 minutes. I can use all those 10 minutes. So I wanted to come back to this issue that I mentioned early on, that people have suggested that if you use a model that has carryover effects in it, you pay a price for that in terms of the variance expression for the estimator of tau A minus tau B. The variance goes up. This is what people have said. And I wanted to show you that that's sometimes true and that's sometimes not true. And this is work that I did with a former student at Oscar published in Statistics and Medicine. So the expression of the variance, tau A hat minus tau B hat, I'm going to write it as V times sigma squared divided by n. So I'm going to use one of the models that we saw earlier, like the model with no carryover effect, the traditional model, small ms, the model m, the model s, and the model with a proportional carryover effects taking that is equal to 1/3. And in all of those cases, that variance, you can always express it in this way, V times sigma squared divided by n. V is what I'm going to show you the tables here, and n is the total number of subjects in the study. They're soon to be equally divided over sequences in the design. I've only shown a few selected designs here, what this number of V is. But for the model with no carryover effects, that's the ideal. That's the ideal V. That's the best you can do. There are no carryover effects. And so what people have suggested is if you use a model that does have carryover effects, this value of V will go up. And is that true? Well, so here is a design ABA for 3 periods. And again, the limitation for designs is the same, so we do 2 sequences using E often. No carryover effects. That number V is equal to 1.5. And yes, it goes up for a traditional model. It goes up to 6. So it's right. There's a huge increase here, a 4-fold increase in terms of the variance expression. Not on every model. Model S is only 1.5. Moreover, if you use a different design, if you're smarter about the choice of design, then there are other models where the increase is actually not all that great. Not at all here. For this design, the idea of 1.5, you still get that under the traditional model. There's no increase at all. This design, as you saw in the previous table already, is not so good under this model because you can't estimate that way nice. But under these other models, again, there's not much of an increase, if any at all. So that statement, you can read down these other rows in this table as well. For example, with 4 periods, the ideal number is 1, and sometimes you actually get that ideal number depending on the combination of the design and model. So sometimes there's no increase at all. So as a general statement, the statement is not true. There are, of course, exceptions, especially if you look at the column here for this model MS. There's always a huge increase. Here you compare these numbers to 1.5. Here you compare these numbers to 1. There's always a huge increase. So there's always a huge price to pay if you use that particular model. And therefore, I would generally not use this model with the This must mean the time is up, right? So the only time that I would use this model is if I were really certain that this was the right model to use. Because if it is the right model, then what will happen is that I get a much smaller sigma squared also. Is an estimated experimental error will become much smaller if it's the right model. And that will make up for this increase in V. Because right now, when I'm just looking at this number V, I'm forgetting about sigma squared. But hopefully, by including carryover effects in my model, I also reduce the experimental error variance and wind up with small sigma squared. But that's not compared to this particular table. So I would be very careful using this model. Only if I really know for certain that that's the right model, that's when I would go to use that. Otherwise, we want to avoid it. Okay, so let me try to come to a conclusion here. I have some other observations about this. I had something about subject dropout. I think I don't really have time to talk about this. So let me just conclude with a summary down here. So, briefly talk about washout periods. Yes, there are critical crossover designs, and there's a possibility of carryover effect. You do want to use washout periods, but it's not guaranteed that washout periods will wash out the treatment from the subject. ABBA design, I agree with the recommendation there that you should only use that if you're certain that there is no carryover effect. Because if there's any carryover effect, you're in trouble with this design. With fixed subject effects, if there's carryover effect, you cannot estimate the difference between treatments A and B. With random subject effects, if there is carryover effect, then really you can only use the data in the first period to estimate the difference between treatments A and B. In some sense, you have to ignore whatever happened in the second period, because that's polluted by the carryover effects. So this design, you really should only use it if you know that there is no carryover effect. With 3 or more periods, where the tables that I've shown you is show that it's important to make a judicious selection of the design. If you know which model you want to use, then that you're going to use, then you know exactly the tables will tell you which design is best. If you're not quite certain about which model you want to use, at least you can pick a design that is relatively robust, that does relatively well on the variety of models. I've only shown you results for 2 treatments, but similar tables can be built for more than 2 treatments. The model and as I said, I would be reluctant to use in general without patterns, and it's really the appropriate model. And I haven't spoken about Java, so I'll leave it out and somewhere there as well. And I'll stop there, and if there are questions, I'll be happy to try to answer. Thank you very much.